Okay, so we're going to do the analysis video for the last lab. So we have two parts. We have the vibrating string and we have the transformer. So let's start with the vibrating string. So we here are at the beginning, and we're going to double click on the tab, and we're going to call that by vibrating string, and this will be where the data is. Okay, now you have this quantity, which is the unstretched mass per length, which is what I gave you. So what we did there is I measured the length of a sampled string, and then I measured the mass, and I divided it out. And we got 0.004, and the units were kilograms per meter. I'm going to double click right here between A and B so I can make this a larger width. Then we had the distance between the supports. Now these are going to all be different for the different setups. So there's going to be 3 different numbers depending upon who you are. The data I'm using, it was 60.25 centimeters. So it should be around that, 50 to 70. And the wavelength of the fundamental frequency is equal to 2 times the length between the supports. And let's go ahead and convert that to meters. So we'll go up here to the equation, do divide by 100. So that is in meters. So the distance between the supports was 60.25 centimeters, or 0.6025 meters, and multiply that by 2, and that gives you the wavelength of the fundamental frequency. Okay, down here we have the masses on the hangers. And let's actually put that, just put mass on hanger. We'll convert that to a tension in a second. So we have the 50, we had the 150. Now some people are going to have different. They may have the 350 but not the 450. The set of data that I had was 450. So we ran 4 out of the 5 masses. So we'll put those in, whichever one's appropriate. Then you have your overhang distance. So that is in your table at the bottom. We'll put them in as centimeters. So I had, with just the hanger, there was 6 centimeters with the hanger and an additional 100 grams. It was 9.5 for the 250 and 28 for the 450. So you should see numbers similar to that. Again, they're going to vary with the setup. Now the total distance is the total distance of the cord that is used so that we can calculate the mass per unit length as the cord stretches. So we're going to say equals, we're going to click on the distance between the supports. We're going to push F4, so that number stays the same, and then we're going to add the value here in cell D7. And I have to, because of where this is, I have to actually put in D7. So we get 60.25 plus 6, and that doesn't add up. So what's going on here? Oh, it's B7, sorry. B7. So you get 60.25 plus 6 is 66.25. Now we can copy that so that it just adds these 4 numbers. That gives me the total length of the stretched cord. So all we have to do is find the mass per length. This is for the stretched cord in kilograms per meter. Is we're going to take this number, 1.004, and we're going to multiply by the difference between the length here, which is the length with very little mass on it. So at 50 grams, it doesn't stretch hardly any at all. So what we're going to do is we're going to take equals. We'll take the mass per unit length, push F4 to get the dollar signs, multiply by the stretched length, which in this case is B8. Now that's going to be updated, and we're going to divide by B8, but we're going to push F4 because we're going to divide by the same number. Or it might be the other way around. Let me think about that. I think it's the other way around. So let's do B8, F4 divided by B8. So we'll see what happens here. So here you get the same number. There's no change because this is the unstretched length. Now what it should happen is this thing gets longer, the mass per unit length should get smaller. So if that's what happens, then we've done it right. Okay, so that's right. So you can see when we have the 450 gram, the mass per unit length is now reduced down to 0.003, because that's the one that's important as far as calculating wave speed. Okay, so that's the mass per unit length. Now to calculate the wave speed, we need the tension, and that is in newtons. So how do we do that? Well, this mass here, the hanging mass plus the hanger is a mass. It's in grams, so we're going to have to convert that to kilograms. So we do equals, click on this cell. We're going to divide by 1,000 to get into kilograms, and we're going to multiply it by 9.8 because weight is equal to mass times gravity. And then we just copy this over. So as we add more mass, the tension should increase. And it does. Okay, now the wave speed in meters per second, according to theory, is equal to the square root of the tension divided by the mass per unit length. So that's the wave speed for the lowest tension. And as you increase the tension, the wave speed is going to increase. Well, as the tension increases and the mass per unit length decreases, both of those result in a higher wave speed. Okay, now this is the predicted fundamental frequency. So remember that is, we've got the wave speed. So wave speed equals lambda times f. So if we want to get f, we take wave speed and divide by the wavelength. So we want to get the wave speed divided by the wavelength. Well, the wavelength is the distance between, oh, it's up here, right? Now that doesn't change, so we put a F4. So we get a predicted fundamental frequency of 9.2 fundamental frequency. Now on your data sheet, we actually measured the fundamental frequency, and this number turns out, at least with the data from the first week, turned out to be much lower than I expected. So I don't know why that is yet. The second week I'm going to try to configure it so instead of having that cord hanging over the actual rod, I'm going to try to get a pulley so that we don't have any issue with not fully transferring the tension from the hanging weight to the tension of the cord. So that's the way it is right now. It doesn't agree. It does. What we do see as you increase tension, you do have higher frequency, fundamental frequency. So that agrees, and we'll find out that they agree in terms of how much they increase when you go to the higher harmonics. So the harmonics agree. The thing that doesn't agree is the predicted fundamental frequency and the actual fundamental frequency. Again, maybe the second week the numbers will agree a little bit better. Now over here we have the actual measurements of the, not just the fundamental frequency, but the harmonics. So again, we had three conditions. We had 50, well, four conditions. Again, yours may be, you may have a 350 in here instead of a 450. and we measure the first harmonic, the second harmonic, third harmonic, fourth harmonic, fifth harmonic. So this is in the table, I think on the top of the page. So again, this is from, I'm going to pause here and fill this table out. So you should have numbers similar to this. Okay, so I filled it out. So with the least mass, the fundamental frequency is around 5. And then if you look at the harmonics, they should be approximate multiples of 4.9. They're not exactly. And then as you increase the mass on the hanger, you get more tension. That higher tension gives you a higher wave speed, and your fundamental frequency increases according to that. So that is the harmonic information. Now we're going to do a couple of graphs. So let's see what I have here. So what I'm going to do is a graph of predicted fundamental frequency and actual fundamental frequency. So we're going to plot, this is going to be the X value, and this is going to be the Y value. Now this is a little different because we've got the things in horizontal rows instead in rows instead of columns. But we can still do that. So let's see how we do it. Okay, so we're going to insert chart. And actually let's push escape there. Let's highlight these two. Well, actually what it's going to do is it's going to think there's 4 things to plot. We only really want to plot one thing, so let's not do that. Let's just pick nothing and just get a blank slate to start with. Now I'm going to just move this to the side for right now so I can see what happens as I choose the data. So the data, the X data is going to be the predicted fundamental frequency, which are these 4 numbers. And the actual frequencies are going to be these numbers. And we don't really need to put a series name because there's only one series. Now I don't know why there's this little blue curve here, so let's just say okay. Okay, let's get rid of that. You may not have even gotten it. So what you can see is that here are the predicted frequencies and here are the measured frequencies. Okay, now that I've got the data, I'm going to right click, move the chart, create a new sheet, and I'm going to call that harmonic. We'll call it fundamental F prediction. So that's a graph. And if we can then fit a curve. So let's click on the data. It's highlighted now. Then right click, add trend line, choose linear. Let's go ahead and put the equation on the chart. Okay. Let's see what else we're going to do. Let's click on the chart. Go over here to the little plus. We want an axis title. We want a chart title. We've got the trend line. We don't need a legend because there's only one thing. I think that's it. Okay. Now we just need to label this thing. So the chart will just say predicted versus, actually let's do measured versus predicted. Measured versus predicted fundamental frequency. So on the x-axis we have the predicted, which are a lot higher than, so it's predicted frequency, the units are hertz. Let's go to the vertical axis, double click in there. So that's the measured frequency in hertz. And that's about it. We just need to change the sizes here. So let's make this to something bigger so we can see it. Make that bigger so it stands out a little bit. Make that one bigger. And we'll make the equation bigger too. And I didn't mean to move that, so let me undo that. Okay, so what that's basically saying is our prediction stinks, or there's something missing here. You know, hopefully we'd have y equals x. That would be the ideal situation. But for some reason it's not working out. And I don't know exactly why, and I haven't figured it out yet. But if I figure it out, I'll let you know. But, you know, we're just trying to analyze, we're just trying to learn some Excel stuff here. Okay, so that's the first graph. The second graph is to look at the harmonics. So we're going to basically be plotting this information. And in this case, it is actually in the right order. So what I'm going to do is I'm going to highlight everything, including the headings. And the headings will be used for the series names, hopefully. Actually, let's stop. Let's push escape there. So let's go ahead and put grams in here so that hopefully it'll insert those words as well when it comes to the legend. Okay. So those are the three tensions. And so we'll highlight that data. We could insert chart spreadsheet. Oh, look at that. Works out perfectly, doesn't it? One thing it shows me is I think I've entered one of the data points wrong, so we'll go look at that. But we've got the data as we want it. So let's right click, move the chart, create a new sheet. We'll call that vibrating string harmonics. So given a measured fundamental frequency, how did the higher order harmonics match up? So this one here, you can see the 250 gram. Why didn't it do 50 grams? We must be missing. It didn't quite do it right here. So let's go to select data. There's a couple of things. Let's look at the data first. So it's at the second harmonic, 250 grams. Second, oh, there we go. So that number's wrong. I think it's 15.6. Let me just double check here. 15.6. Okay, now let's look at the data. Okay, so that looks a lot better. Now, again, it looks like I'm missing one of the things as far as the graph is concerned. Okay, we want to go to data. Actually, why isn't it? I'm trying to figure out why it's not showing me the, oh, here, design. There we go. Select data. So you see it doesn't have the 50 gram for some reason. So Yeah, what I'm going to do here is I'm just going to remove them all and start all over again. So series 1 is 50 grams. Then we go to the data. So this is 50 grams. Oh, I know what happened. So the problem here, yeah, I just realized I forgot to do one thing. So let's cancel this thing out. We need to insert a column. So I'm just going to put numbers in: first harmonic, second harmonic, third harmonic, fourth harmonic, fifth harmonic, instead of using F1, F2, F3, F4, F5. So that will give me my X values. These will be my X values, and then I'll have Y values for each one of these. So let's go back to the graph. Go to design, select data. I'm going to again remove all the data. Start with a clean sheet. Okay, now series 1, 50 grams. The X values. Go down here to the data. The X values are always going to be 1 through 5. The Y values are this column. So we got 1 through 5 and then these numbers. So you can see the first set of data. Then we'll add a second set of data, which is going to be 150 grams. The X values are, again, 1 through 5. These are the harmonics. The Y values will be the ones under 150 grams. So I get my next set of data. My third one will be 250 grams. Again, you're going to match these up to whatever things you measured. Okay, so go again here, same X values. Y values are the 250 grams. So that's the next set. And then finally, in my case, it's the 450 grams. You may have 350 grams. Click on there, click on vibrating string, highlight 1 through 5. Click on the values under that thing, and you get that. So now we can say, okay, we've got all the data. So on the x-axis are the harmonics, on the y-axis are the frequencies. Before we put the labels, let's go ahead and put trend lines for each one of these. Now we don't need to, we're not going to come up with the equations. So add trend line, linear. Okay, we're done there. Okay, next thing is click on the next set of symbols. Right click, add trend line. Click on the next one, the gray ones, right click, add trend line. And then the fourth one. The important thing here is you can see that the data has a pretty good prediction, linear prediction, as far as the harmonics are concerned. It's fairly consistent, predictable. That's what we like in physics, is predictable. Okay, now let's clean this thing up. So we're gonna plus. We're gonna need axis titles. We need a chart title. We'll leave the grid lines. We have a legend. Let's move the legend. So if we click on legend here and go to top, I like that better. Okay. Now we just need to put some titles here. So we'll just say harmonic frequency measurements. So that's the title, chart title. The axis title is going to be harmonic number. So first, second, third, fourth, and fifth. The axis title here is going to be frequency. Did I spell that right? Frequency, I think so. The units are hertz. Okay, let's make the sizes as we normally do. So we're going to make that one 14. Make this one 14. I forgot to change the font of the actual numbers, but that's okay. We'll just leave them small. So there's our graph. We've got a legend, we've got curve fits to them, linear fits, we've got the label axes. So that's it. So that looks pretty predictable. So that's all we're going to do for that. Okay, now we're going to add another sheet, and this is going to be the transformer data. So that's transformer data. Now with transformers, let's find out what I had here. So we didn't have as much data. We basically had a step down transformer. That was the that's the first thing that we did. And we had the input voltage and we had the output voltage. Okay, so we had the step down transformer. The last one was a step up transformer. So we also had input voltage and output voltage. And then we looked at the effective frequency effect. And there we had frequency that we changed. We had an input voltage of 5 volts. This was a step down transformer. So the first entry for the step down transformer is the same first entry for the frequency. So here's my data. So we had 5 volts, 4 volts, 3 volts, 2 volts, 1. Those were the input voltages. And the output voltages I got were 0.234, 0.188, 0.14, 0.093, and 0.047. So you can see the output voltage is lower than the input voltage. For the step-up transformer, we had low voltages as our input, and our output voltage was higher. So I got 0.449, 0.913, 1.848, 2.769, 3.574. And then for the frequency data, we had 60 hertz, 50 hertz, 40, 30, 20, 10, and 5. And so the first value here, 0.234, here is the same because these are all 5 volts. Frequency one was input of 5 volts. So at 60 hertz, which is what we ran the step-down transformer at, we got 0.234 volts. Okay, so what we see is a gradual decline in voltage. So it actually steps down even further. Now, one thing we don't measure is efficiency, but we do see how the output voltage gets lower. So that's the input data, and you'll input your data. So you have your step-down transformer, your step-up transformer, and your effect on frequency. So what we're going to do is we're going to plot these 3 sets of data. So the first one is this. So highlight those 10 cells. We'll go to Input, Insert, Scatter Plot. There it is. So that looks good. So let's right-click, move the chart, and we'll call that Step Down Transformer. And you can see a nice linear relationship. So it's predictable. Again, we like predictable in physics. Let's add a trend line. And we will include the equation on the chart. Okay, click on the little plus sign. We want some axis titles. We don't need a legend. We don't need error bars. So I think that's it. So what we have is chart title is step down transformer. We could put down, details about the size of the coils and all that kind of stuff, and we're measuring voltages. along the x-axis we have the input voltage, and the units are volts. And then on the y-axis we have the output voltage. Also in volts. Okay, let's change the size of these things so we can actually see them. Okay, and the equation. So what you'll notice here is the slope of the line is how much it's stepping down on average. And because it's a nice linear relationship, it's pretty much the same amount for each level. So it's very consistent. So if you take if we take 0.0469 and we take the reciprocal of that, we'll get 21. So it's a factor of 21 that the voltage drops. Now we'll find out that that's different than the step-up transformer. And in the theory, it says that it shouldn't make any difference whether you're stepping up or you're stepping down. It should be the same number. It's just the ratio of the number of loops. And the actual ratio of the number of loops is, I'd have to look it up for those particular coils, but I think it's more like 12. So it actually steps down more than you would predict from theory. Again, I'm not going to try to explain why everything doesn't match up perfectly. Actually, instead of creating a whole new graph for the step-up transformer, let's try to use as much as we can here. So what I'm going to do is I'm going to click on the tab, step-down transformer. I'm going to right-click. I'm going to move or copy. I'm going to create a copy, and I'm going to put it right where the step-down transformer is. So what it does is it creates this new tab, step-down transformer 2, which is an exact copy of step-down transformer. So I'm going to change this. So we'll double-click on the little tab, get rid of the 2 part, and we'll change down to up. What this allows me to do is it allows me to reuse everything. All I have to do is just to make some changes. The output voltage and input voltage are going to be applicable. And because we automatically scale this thing, we're not going to have to change the scaling. It'll do it automatically for us. The trend line is probably not going to work, but we'll see what happens. So what we do is we click on the chart, we go to Design, we select Data, and we edit the data. So right now it's using A4 through A8 and B4 through B8. So if we click on that and we highlight these values for the X values and these values for the Y values, everything should be great. The only problem is the trend. Well, no, actually, what happened here? Well, that didn't work. Let's go back and do that again. We could just remove it. Let's remove it instead of trying to edit it. So what we'll do is we'll go back and we'll pick the data. So the X data is the lower voltages here, and the Y data is this data. And then we'll say OK. And we see we've got a number that looks fishy. So let's go check this out. Oh, this should be 0.05. Step up transformer. Okay, now everything's looking good. So the only thing we have to put a new trend line on there. So let's click one of the data points, right click, add trend line. So again, it's a pretty predictable result. Nice linear thing. We'll choose display the equation. You see it's about 9. Before we got around 20 going the other direction. So we don't have to change any of the sizes except for the trend line. We need to make that 14 so I can see it better. And finally, we need to change this to a step-up transformer. So I think everything's consistent now. Output voltage, input voltage. So you can see how the output voltage is bigger than the input voltage. Our equation is the factor is about a factor of 9, whereas when we had the step-down transformer, we had a factor of about 20 going the other direction. And I think the number of loops is somewhere, the ratio of the number of loops is somewhere in the middle of those two things. Okay, and then the final thing is this frequency. So we're going to just treat that with, and we'll just do a new graph for that. So we'll highlight the data. We'll insert chart. So there it is. So on the x-axis we have frequency, and on the y-axis we have the voltage. So we can right-click the chart, move the chart. We'll call transformer frequency. So now we have a separate graph. We're not going to try to fit a curve because it's obviously not linear. And we'll need to add the ability to add axis titles. We only have one set of data, so we don't need a legend. We're not going to trend lines, so we're all set there. And all we have to do now is put some axes labels. So that's frequency in hertz. On the x-axis, on the y-axis, we have output voltage in volts. The chart title is transformer performance as a function of frequency. And then we'll just change the sizes back to our normal size things here. So we'll make the axis titles 14, chart title 16, and there we're done. So again, what we see is this, you need a certain level of frequency, 40 to 60 hertz, to have this thing operate efficiently. At lower frequency, it doesn't work. When it comes to the step-down transformer, we get a larger difference than would be predicted by theory, and for the step-up transformer, we get less of a performance. So it's not behaving ideally. So that is it. You've got your vibrating string data. You've got how the harmonics, the measured harmonics, compare with each other, and how the increased tension increases all the harmonics predictably. We did see that the measured and predicted fundamental frequencies don't match up well with the data from the first week's group. We'll see how the second week's group does. I'll probably go ahead and just take this and put in a new set of data, and then I won't have to do anything. You know, once you have this set up, you can just enter data and everything will get updated, except for the trend lines, and you've usually got to update the trend lines. And then from the transformer perspective, we looked at both step-up and step-down transformers and how frequency affected. So that's what you're going to turn in. Let me save this. So this was what I did earlier. So this is a new one. And we're done. Okay, so here is the correction. So the distances here were actually in inches. And therefore, I need to take the value here that I had before So 2 times the length times 100, I've got to multiply by 2.54 inches. So that is the predicted frequency. Now, the remainder of the stuff here is just the ratios of distances, so I don't really have to, I'm going to check I'm going to put the units correct here. So the distances are actually in inches. So when I adjust the mass per unit length, due to the stretch, it's still the same numbers, and it doesn't have to be converted. But when it comes to calculating the wavelength, I've got to convert that to meters. And I realized that today when we were doing the lab the second time, because I thought that's almost 1.5 meters. It's not 6.6 meters. And I'm like, oh yeah, that's right. We measured in inches. So I don't think there's anywhere else that we have to worry about that, because of the other ones we just measured the distances. I mean, we measured the frequencies. So now if we compare the fundamental frequency prediction here, you see it's closer. That's still not exactly right. It's 0.69 instead of 1 to 1. But at least it's a little bit closer. Kind of flipped the other way around. So I'm not sure why that difference exists, but it's at least closer to the right answer. So that's the correction. Just convert the wavelength to meters by multiplying the formula by 2.54, and everything else should update automatically.